We're going to talk about a very interesting family of groups called dihedral groups. Okay, these groups are the symmetry groups of regular polygons. I'm going to think of it somewhat graph theoretically though. So I'm going to think of the nth dihedral group as the symmetry group of the n cycle. So let me define for you the nth cycle graph. So this is a graph gamma n. Vertex set is just a set of integers from 1 to n, and the edges are 1 comma 2 is an edge, 2 comma 3 is an edge, and so on. N minus 1 comma n is an edge, and then n comma 1 is an edge. Okay, so it's got n vertices and n edges, and let me just draw an example for you. Gamma 6 is going to have 6 vertices and 6 edges joining them. Right, so I'll call these vertices 1, 2, 3, 4, 5, 6. Now, what's the order of the group Dn? So I'm defining Dn to be the automorphism group of the graph gamma n. So this is called the nth dihedral group. Or, well, okay, so what's the order of Dn? So the order of Dn, we've seen already how to compute this. We did the example for D4 in fact when we looked at the automorphism groups of the square. So the order of Dn is the number of elements in Dn that fix the point 1. So this is W in Dn such that W of 1 is 1, and so times the orbit of Dn, so Dn dot of 1 in Dn. Okay, so we're using this result from one of the earlier lectures, and so we asked, okay, what are the elements of Dn which take 1 to 1? So if you have to take this point 1 and map it to itself, what can you do with 2? Either you take 2 to itself because it has to go to a point that's adjacent to 1. You can either take 2 to itself, or you can sort of take 2 to 6, and so you'll get a reflection about this axis. Okay, so this group Dn stabilizer of 1 in Dn has 2 elements. First is just the identity element, and the second is this reflection. So it takes 1 to 1, it takes 2 to n, it takes 3 to n minus 1, and so on, and it takes n to 2. It interchanges 2 and n. It interchanges 2 and n, it interchanges 3 and n minus 1, and so on. Okay, so that's the element. I'll just call this element S. Okay, so this is the 1 comma S. And what is the orbit of 1? Well, you can take this graph and move 1 to 2, then 2 to 3, 3 to 4, 4 to 5, and so on, and 6 to 1. So that's a rotation by 60 degrees in the case of the hexagon. In general, you can rotate in the hexagon, you can rotate by multiples of 60 degrees. Well, so here what I want to say is that Dn consists of 1. Let me introduce a special element in this group. We'll introduce the element R, which is given by 1 goes to 2. Oops, I'll write it in one line notation. 1 goes to 2, 2 goes to 3, and so on. N minus 1 goes to n, and n goes to 1. So R, of course, takes 1 to 2, r squared takes 1 to 3, and so on. And some power of r will take 1 to any of the numbers 1 to n. So the orbit of 1 is all the vertices of the graph. So if you apply this equality, what you get is 2. This is this order of the stabilizer of 1 that has 2 elements, and then you multiply by n. Okay, so the nth dihedral group has 2n elements. Okay, I'm going to try to write down these 2n elements. So I'm going to make a table here. So firstly, I have this element identity. Every group has an identity element. So this is just the identity permutation. Then I have r, I have r squared, and so on. I have r to the power n minus 2, and I have r to the power n minus 1. And then r to the power n is equal to the identity. Okay, so these elements are what are called rotations. And I also have this element s, right? So this takes the identity to the identity, but it is in fact a reflection. Okay, but there's some more elements. You know that a group is closed under composition, so I can ask, okay, what if I first apply s and then apply r? So I'm looking at the element rs. So let's see what rs does. So it takes where does it take 1? rs takes 1 to well, so let's see. S takes 1 to 1, so this takes it to r of 1, so it's 2. Okay, and this is not a rotation, it's a composition of first you reflect and then you rotate. So it turns out that this is again a reflection. We'll figure out exactly what kind of reflection later in the exercises. Okay, and you can also do r squared times s. And where does this take 1? Well, it take again s of 1 is 1, so this goes to r squared of 1, which is 3. So on rn minus 2 times s and rn minus 1 times s. So all these elements here, what is the image of 1? So both these elements take 1 to 1. These elements take 1 to 2. These elements take 1 to 3. This guy takes 1 to n minus 1, and this guy takes 1 to n. Okay, so we've written down, we know that this column has rotations, this column has reflections, and the image of 1 is different for elements in different rows and columns. So these 2n elements that we've written down here are clearly distinct elements of Dn. So and we know that Dn has exactly 2n elements. So what we've done is we've enumerated all the elements of Dn. Now but we can also try to work the other way. What about s times r? Okay, so s times r is first you rotate and then you reflect. It turns out that this is also a rotation about some other axis, and so if it's going to be one of these reflections here. Which one is it? To figure out which one it is, we just need to see what it does to 1. So what is SR of 1? Well, that's S of 2, and that's what's S of 2? S of 2 is well, S takes 1 to 1 and takes 2 to n, so that's n. So this must be S times R. Okay, and let's look at SR of 2. sorry, S not R of 2. What I want to look at is S R squared of 1. Okay, so this is S of 3, but that's n minus 1. So this is S R squared, and as you can guess, this will go the other way. This will be S R to the n minus 2. This will be S R to the n minus 1, and this will be S R to the n, but R to the n is identity. This is just S. Okay, so these elements can be written in two different ways in terms of R and S, if you like, depending on whether you want to apply R first or you want to apply S first. Okay, so what we have here is a relation in the group which is R to the power n minus I S is S R to the power I. Or if you put I equals 1, then you're just saying that S R is equal to R to the n minus 1 times S. Okay, so what we are seeing is that okay, so let R be the set of all elements of the form. Maybe I'll call it Rn 1 identity, not 1. Let's call it identity. Sometimes I write 1 for identity. So identity R squared R to the n minus 1, and then R to the n is back to the identity, and then S is the subgroup identity, and this element little s. Remember, little s is the element which takes 1 to 1, 2 to n, 3 to n minus 1, and n to 2. So both Rn and S are subgroups of Dn. Okay, and moreover, this identity that S R to the I is equal to R to the n minus I times S, this can be written as S R to the I S inverse is equal to R to the n minus I. Note that S is a reflection, S squared is the identity. So S is equal to S inverse. We can also write this as S R to the I S is equal to R to the n minus I. So whichever way you look at it, what you get is S times Rn is Rn times S. So this subgroup Rn has order n. Dn has order 2n, and Dn is Rn disjoint union with SRn. This SRn is just a left coset of Rn, but it's also a right coset of Rn. So Rn is a normal subgroup of Dn. Okay, when we say something is a normal subgroup of something, we write it like this. A triangle pointing towards the smaller group. So Rn is a normal subgroup of Dn. Okay, so here let's just make a few observations about what we've discussed. We have this group Dn has two subgroups. Rn and S. Okay, and then Rn is normal in Dn, and thirdly, every element of Dn can be uniquely written in the form G equals U times S, where U belongs to R and S belongs to. Maybe I shouldn't use S because S is a specific element, S epsilon, where epsilon belongs to S. Okay, this last property, well, it's illustrated here in this table, right? So these are the elements where epsilon is equal to 1. These in the first column, the rotations, and the reflections are the elements where epsilon is equal to S. So, but every element has a unique expression where has a unique factorization, two factors, where the left factor is in Rn and the right factor is in S. And we can also write it the other way, that it can be written as epsilon times U. So under these circumstances, we say that Dn is a semi-direct product of Rn and S. We write Dn is equal to Rn. Now Rn is a normal subgroup, so that symbol is just slightly changed. S. This Rn is just isomorphic to Z mod Nz, and this S is isomorphic to the cyclic group of order 2, which we can call Z mod 2Z. And so this basically, this group, dihedral group Dn, can be constructed from two very simple groups, the cyclic group of order n and the cyclic group of order 2. This is a general construction called the semi-direct product construction. So what we have seen here is an internal semi-direct product. We have a group, we have two subgroups, and we have said when this group is a semi-direct product of these two subgroups. But we can also think of this as a construction of new groups from old. Okay, we'll look at this in the next recording. I'll stop here for now.